Okay, section 1.14, recognizing patterns. Okay, this is actually kind of not that bad of one, not that bad of a section. Okay. All right, let's look at the Explorer. It says consider the sequence of numbers 2, -4, and they want us to come up with the next three numbers. Well, there's going to be different ways of doing these. I'm just for me, I'm looking at this. I'm just multiplying this by -2. So if I multiply this, make sure that they don't repeat this two more times. Yeah, sometimes they give us rules that we have, but this time we don't. So if I multiply 2 by -2, so I'm going to multiply by -2 to get -4. So if I multiply -4 by -2, I get +8. If I take +8, multiply it by -2, I get -16. Multiply it by -2, I get +32. Okay. So I guess I was supposed to write those down here. So the first rule I came up with, let's see, I had 8, I had -16, 32, and I was multiplying the first number by -2. And now they want to come up with another rule or a different rule. So one way I can get from 2 to -4 is I can actually subtract 6. So what if I subtract 6 from the first number? So 2 minus 6 is -4. So I do that to -4. -4 minus 6, -10, -10 minus 6, it's -16, -16 minus 6, it's -2. Okay, so the rule I used that time was subtract by 6. Let's come up with another rule. How else can I get from 2 to -4? Well, I multiplied, I divide, so I have a couple of things I can do. I can add or I can divide. Now, divide would be a little bit difficult because I'd have to do some figuring, probably have to divide by an improper fraction. Let's see. I could kind of cheat here by using, see, I subtracted 6. What if I added, instead of subtracting 6, I add -6? Okay. So 2 plus -6 gives me -4. And I'm going to get the same sequence here, right? -4 plus -6, -10, -10 plus -6, -16, and -22. Oh, I forgot the 2 up there. So I came up with 3 rules, 3 different ways, and I kind of took the easy way out between B and C. Okay, so let's see what we got here. It says, in human nature to generalize patterns. That, by the way, that's pretty much what mathematics is. It's generalizing patterns. That's what algebra is. That's why we have those unknown variables, because we like to generalize formulas so that we have stick any value in for that variable. It's often necessary in this course to write expressions, generalize patterns, and write expressions too. Can you? Okay. Well, let's keep going on here. We will often need to look at a list of numbers and make a guess about the pattern that exists. This skill can help us create models, graphs, and projections for the future. The process of making an educated guess or a conclusion based on the evidence provided is known as conjecture. And hopefully, you guys went through this in geometry. Okay, so conjecture is an educated guess or conclusion. For instance, when we look at the Fibonacci sequence, It's a sequence of number. It's famous. Uh, it's got a pattern, and you'll see what the pattern is in a minute. Okay, so um, it says write the next 6 numbers in the sequence and describe the rule that you're using. Okay, so let's see. Here I start out with the number 1, and then I have another one. So it looks like I added the number before that was actually 0. So 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 plus 8 is 21. 21 plus 13 is 34. Plus 21 is 55. Plus 34, see, 9, 89. So that's actually the Fibonacci sequences. You add the number before it. Okay. A sequence begins with the first term, followed by the second term, and so on and so forth, until we get to the nth term. So we have to make a generalization here. Eventually, we're going to make a mathematical formula eventually for the nth position, and then we can just say, okay, in the 12th position, that number is going to be whatever the sequence is. And number 3, determine the pattern in the following sequence and write an expression for the nth term. It may help to label the term number for each term to see the relationship between the term number and the values in the term. Okay, so let's see what the rule is. Okay. Let's say it's got 3 halves, 4 thirds, 5 fourths, 6 fifths. Okay, so this is term number 1. Term number 2, 3, 4, and 5. And then we're going to have this nth term that we need to make a formula for. So between the first and second term, it looks like I'm increasing the numerator by 1 and increasing the denominator by 1. Well, my rule is increasing the numerator and denominator by 1. Now, how can I describe that for the nth term? Well, for the nth term, I'm going to take the previous term. So if this is the nth term, so this is term number 1, 2, 3. This is the nth term. So here's n. That's the nth term because this is the first term, second term, third term. The nth term here is n. So what I do is I take the previous term. So the previous term from n is going to be, well, I don't know what it is per se as far as number wise, but I know the value is going to be that n term minus 1. Okay. So that nth term is going to be n minus 1. Okay. And then I'm going to have to add the 1 back in there. I'm sorry, I'm going to have to add 2 because if I add 1, I get back to n. And then if they want the next term, let's see what this is. Between the nth term. So no, we're good. We're good with n. So we're just going to take n and, okay, I'm going to write this a different way because eventually we're going to have a formula and a way to make up an equation using the nth term. So let's just consider the nth term. That's going to equal the previous term, and I'm going to go back to that n minus 1 for the numerator and the n minus 2 for the denominator, because that's the term that's going to be right before the nth term. And to get from this term to the nth term, I'm just going to add 1 over 1, or 1 to the entire thing. So I'm going to leave it at that simple stage, but it's going to be a little more difficult when we actually put it into an abstract thought. Okay, next page. And again, hopefully this is review from geometry. There's two types of reasoning that you studied in geometry. One is known as inductive reasoning, and when you move from, which is just a general rule, and when we move to a specific case, we use deductive reasoning. Since both types of reasoning are often in our daily lives, we have trouble distinguishing. Inductive reasoning is used to form a hypothesis, right, or conjecture, and then deductive reasoning is to prove the conjectures. Okay, so deductive, you're going to prove what you came up with. Okay, for example, you might conjecture that squaring a number always produces a positive result, since 1 squared equals 1, 2 squared equals 4, and so on. However, that rule gets broken when we look at the number 0 squared. 0 squared equals 0, which is not positive because 0 is neither positive nor negative. This counterexample disproves the conjecture, because it shows a case in which squaring a number does not produce a positive result. Again, 0 is neutral. It's neither negative nor positive. So as soon as you get one counterexample, your conjecture or hypothesis is wrong. And here it goes on to explain it here. Only one counterexample disproves a conjecture. However, a conjecture cannot be proven even with multiple examples. Instead, a conjecture can be proven only with deductive logic. Okay, let's look at their example. A student knows that a number is given if the last digit in the number is even. So she wonders if a number must be divisible by 3. If the last digit is divisible by 3, find a counterexample that proves her conjecture false. Okay, the student's conjecture is that if the last digit is divisible by 3, then the number is divisible also by 3. So a counterexample would be a number that the last digit is divisible by 3, but it is not itself divisible by 3. Try the first 2-digit number that could possibly work as a counterexample. How about 13? This number has a last digit of 3 that is divisible by 3, but the number 13 is not divisible by 3. 13 is a prime number. We do not get a whole number answer that we divided by 13 by 3, so 13 serves as a counterexample to her conjecture. Make sense? I hope so. Okay, let's talk about the two different sequences that you need to know about. Arithmetic sequence. The next term is always found by adding the same number to the previous term. Don't forget, you can add positives or negative numbers. Example, -8, -6, -4. It's an arithmetic sequence because each term is adding 2 to the previous term. So arithmetic sequence, adding. Okay. Geometric sequence, you're going to be multiplying the previous term. Don't forget, you can multiply by fractions, and when you do that, a lot of people think of it as division. For example, -8, 16, -32, so on and so forth. You're multiplying the previous one by -2. Okay, example, -17, -12, -7, -2. Looks like we're adding +5 to each of those. So this is an arithmetic sequence. The nth term is going to be your initial term, your first term. This is the first term. Okay, first term, and you're going to be adding to it the term that's before the nth term, which is n minus 1. So this is the term before the nth term. And that what we actually did was we multiplied that term by 5. Okay. So the first term was -17. We're trying to get to the nth term. Remember, trying to get to the nth term. So our first term was -17. We're going to take the previous term of the nth term, which is n minus 1, and we're going to add to it the number of 5s all the way to the term before the 5. That's why we have a multiplication of 5 here. Number 4, consider the sequence 150, 25, 12, and 5. 12.5. It says describe how each term is generated from the previous term. And is this sequence arithmetic, geometric, or neither? Well, the first term is 100. Do the calculation to get from the term get term from the first term. Okay, so we're going to take the 100 and we're going to multiply. Let's see, we're going to multiply. Take 100. We're going to multiply it by 1/2, and that's going to give us 50. So what we're doing is we're multiplying by 1/2. Okay, calculate to get from this term. So we're going to take 50 times 1/2 equals 25. 25. So term number 3 is to get to term number 4. I'm sorry, to get to term number 4. We're going to actually, we should have put that down here. To get this should go down here. This one should go down here. And for term number 5, we're going to take term number 4 and multiply it by 1/2. And that'll give us term number 5, which is 12.5 divided by 1/2. And I better get a calculator. It's going to be a quarter. Let's see. Or half of 12.4. Well, half of 12 is 6, and half of a half is a quarter. Then to get to the sixth term, I'm going to take the fifth term and multiply by a half. So 6 and a quarter, see, half of 6 is 3, half of a quarter is an eighth, and I think that's 125. Okay, so there's my term. I completed the table. C, write an expression for the nth term. So the nth term is going to equal, let's see, my first term, which was 100,